Morning, or yeah, whatever time zone you're in. How's it going?
What is that background?
Windows. Figured I'd mix it up a little bit. Old school, yeah. Is my name backwards, the YouTube handle, or is it forwards?
No, it's forwards.
Okay, perfect. I always forget on Zoom.
It, it just looks like something out of Tron.
Yeah, cool. I think I might have stolen the background from like a work uh visual like asset kind of folder and then just added some colors in Figma.
Mm.
That's another cool tool. If you all have not uh, checked it out, it's used pretty um, extensively in industry um, across like products and tech teams. They used it at Esri when I was working there. They use it at the
Oh.
current company I work at called Edgenode. It's kind of like a design tool, but it's
Hmm.
not just for designers, and it's super useful. I use it for random stuff. But yeah, I would say check out Figma. It's a cool kind of like buzzwordy tool that if you can do some stuff on it, it's useful for your resume and for jobs. Yeah. So we'll let people trickle in a little bit, and then we'll get started. But we can continue to admire my amazing graphic design skills. Or does that mean graphic design is my passion? Um, it's definitely not. Nothing against graphic design. It's just it's not my. Oh, there we go. This is a good one. Yeah, I'm not a I'm more of a code guy than the design guy. We'll just put it that way. Right. I mean, it's a smaller group today, but I respect that you all showed up on time. So let's just get into it and we'll go from there. Let me figure out which screen to share. My God. How many? There's one, two, six, nine, 11 options on my basic screen share for Zoom. That's peak UX. Sorry, I'm just salty. Uh, so multispectral data with Python. Before we get too deep into the content, we'll do kind of an overview of what to expect for today, which I'll just kind of jump into instantly. The agenda. So course updates like we've been doing the last few weeks. Quick check-in, kind of a follow-up to last week, just to see where we're all standing. Then, of course, the code word, which we're all waiting for, and then the interactive lab walkthrough. And what you can expect for today's lab is really a high-level intro to multispectral data, and then practicing common operations like opening files, cropping files, saving files. Next week, we'll really kind of be digging deeper and using multispectral data to create indices, i.e., spectral indices. But this week is kind of laying the groundwork for some more exciting things next week. But just wanted to set some context there. And then course updates, remaining classes. It's kind of crazy to think about, but we only have two sessions left, one of which is the final. And so we have today, May 4th, next week, May 11th, and then the final is on the 18th. So we're like Naruto sprinting to the finish line right now. And I just want to remind you all to catch up on any late lab assignments that you might not have turned in yet, because you can still get points. Strongly encourage you to turn in late assignments. And then in that vein, these are all assignments that you still have the opportunity to turn in on time. Uh, the one that's most pressing is Lab 4, which is due today before midnight. So you have the assignment from last week. We kind of extended remaining deadlines for all subsequent labs so that you have all of Saturday to complete it as well. So I just wanted to call it out. Don't forget to finish your lab 4. It's due before tonight. Um, Today we're going to be working on lab 5, and so that's due next Saturday before midnight. So again, you'll have, I guess, 8 days to complete it. So I hope that that extra time really does help. Um, and then lab 6, which will start on, I guess, next week, is going to be due the 18th before midnight. So 3 more assignments that we're kind of going to be working through as a class together. And then just wanted to call out the final, which we're going to start on the 18th. That's going to be a little less hand-holdy, but more kind of reinforcing the things that we've covered this semester already. So very similar to previous semester, how it's kind of like a high level overview of can you walk the walk now? I know you can talk the talk. And then there's also extra credit assignments that I've been posting to Canvas or whatever it's called now. CSULBinfrastructure.com. So make sure to check those out. Those are additional opportunities to earn points, and um, they're not due until the 19th before midnight. So you have plenty of time to do those and kind of earn some extra points. And then I see a question from Muniba for the final. Do we have to be on Zoom or can we work on our own time? I'm guessing that's kind of what you mean. Uh, if you have, I mean, ideally, yes, everyone shows up to the Zoom just for a quick check-in to kind of culminate the semester, and then you can work independently. But if you have some kind of prior engagement, whether that's work, school, travel, do reach out as soon as you can. But um, yeah, it's you don't have to be in class on the 18th for the full 3.5, 4 hours. It's really more just a quick check-in, maybe like a goodbye, peace out, let's stay in touch, and then you can do your final independently. Hopefully that answers your question. Yeah, it's been great so far, but we are running to the end. So I do want to remind you all that we are getting close. Um, and I know that you have plenty of other classes, life, jobs, etc. So this is the kind of obligatory or not obligatory, but it should be obligatory. Maybe I'll complain to the department that more lecturers need to check in, but uh, let's do a check-in again. We did this last week, and I feel like it was super helpful. It seemed like you all just appreciated uh, me asking, which cool. Sorry that I'm the first to ask, but how's it going? Um, is it a similar level of overwhelm as last week? Better or worse? Where are we standing? Uh, please don't disparage anyone, but also just be frank about like course load and uh, all that kind of stuff. Okay, so Talissa's fighting a sinus infection. Is there some illness going around the greater Long Beach area? I might be safe in the desert. Yeah, feel free to unmute, put it in chat. I do want to offer this opportunity for you all to share how are you doing with course load? Is it too much? Is it okay? I'm fairly flexible, so this is your opportunity to let me know how you're feeling.
Moving the deadlines really did help, at least to me. Like
Oh,
sometimes I don't have the chance to finish it all in a day.
yeah, no, I hear you. So just keeping it like it is, maybe for another week will be fine. You think that that kind of I guess what I'm asking is, do we need to make more uh, adjustments, or is what we've done so far enough? And if you feel more comfortable not doing this publicly in front of others, feel free to just message me. But I do want to just give an opportunity for you all to kind of voice where you are, because yeah, I'm not living your lives, so I don't know like what's up. So you know what I mean? Also, the world is just like this crazy, like chaotic mess right now, especially with like just things going on campuses and the poor response from administrations generally. And so just wanted to like put it out there that like I know y'all are going through some stuff right now. And yeah, just let me know. Okay. I mean, it seems like the extra time was a big game changer. So cool. I'm glad that's helping. Do reach out if you have additional kind of commentary to add. But yeah, thank you all for those who did comment or unmute. It's much appreciated. Okay, let's oop, there it is. Let's get into the code word for the day. That's why you're all here. No, I'm just kidding. But this is the mighty common creosote bush, I think. Yeah, pretty sure. Larea tridentata. So make sure to input this into Canvas and you'll get some points. Not the most exciting, cool, funky, different plant. I think these are like one of the most common around the Southern California mega region, but important nonetheless. They're all over. Uh, one of the common flora found in California and further around the Western US. And I'll share how that's spelled in chat just to minimize pain. Tridentata. Enjoy. Let's code. So I'll stop sharing for a second and then we'll pivot to course website. So many browsers. So today, let's walk through what we're gonna kind of bite off to chew on, and then we'll walk through the labs like we do every week. So we're going to be diving into multispectral data with Python due before, this is incorrect. It's actually due before midnight. And so, or 11:59 p.m. on May 11th. So I'll update this later, but the canvas will reflect the correct due date. But today, we're going to create a lab 5 repository in our GitHub account like we've been doing each week, using this GitHub Codespaces Jupyter template repo. Then we're going to open that repo in Codespace and create a bunch of Jupyter notebooks and follow these awesome lessons from CU Boulder's Intermediate Earth Data Science textbook, which basically kind of just a textbook that kind of mashes remote sensing, earth science kind of questions with Python data science-y techniques. And now this branding of earth data science. So a lot of it is kind of branding and positioning geospatial analysis in a new way that kind of aligns with marketing hype. But it's also valuable. So we're going to go through a bunch of these lessons, commit changes to our repository as we work through each lesson, and then submit the URL to Canvas. Similarly, there's a Lab 5 extra credit opportunity in Canvas worth an additional 5 points. We'll kind of walk through that if we have time after going through the main lab, but it's very similar content to what we're going through either this week or previous week, and kind of an additional opportunity for you to demonstrate that you can follow developer documentation or guides, and just kind of proving that you're able to kind of walk the walk and not just talk the talk. But those are optional. They won't go against your final grade if you don't feel like doing them, but I'll add them to, or I'll add the points to your final score at the end of the semester. So just wanted to remind you, there's more extra credit. So that's basically half of this whole lab. You can earn an additional 50% extra points. But yeah, before we jump into actually running through the lab, are there any questions, concerns? Again, opening up the check-in, kind of if people are feeling more brave again and want to share. Just wanted to pause one more time before we jump into code. Okay, we'll pause the pausing. Let's go to GitHub. I'm gonna share my GitHub screen now, and that way it's a little easier to follow along with what I'm doing. And then I'll have the instructions kind of separately for myself to follow. Let's create a new repository, but actually we want to use a template repo. So I'm going to share the link with you in a second. We're using code spaces Jupyter. I'll share that in chat, wherever chat is. Cool. So you can grab that link in chat if you need it. It should also just be in your browser history because we've been using the same repo all semester or most of the semester. So let's use this repo as a template repository and create a new repository. We don't need to include all branches, but we do want to create it in our GitHub account. And I'm going to call this GISC 606 lab 5. Yeah. Oh, okay. Not going to put a description because it's optional, and make sure you set it to public so I can view it when I'm grading. And then we'll create the repository. Now let's open it up in a code space. So let's create a code space on main. That'll take a few moments as it's opening up a new kind of like computing environment for us. It's kind of spinning it up in the background. And now we have a nice VS Code style interface to hack away in. So it's going to take a moment. It's going to install some Python libraries from this requirements.txt. It just needs like a minute to wake up, but it'll use pip like it does each week. And there you go. Pip install requirements.txt. Once that's done, we'll create some notebooks to do some Python in. In the meantime, I'm going to open the first lesson for today, Introduction to Multispectral Remote Sensing Data in Python. So it's number 1 for today out of 10. And let's toggle back just to see if it's done yet. It's done. Okay, then I'll do some Python stuff first. So we have our, where did that go? Oops, okay. Let's create a notebook called Intro Multispectral .ipynb. And then we'll click that to open and display it in our view here. I'm just squishing these a little bit so that we have more of the screen dedicated to the notebook. So I'm going to return back to the instructions here, and we'll just jump in. So we're going to learn about various options for multispectral remote sensing data and the advantages and disadvantages of these options. Along the way, we're going to learn how to define spectral and spatial resolution and explain how they differ from each other. We're going to define multispectral or multiband remote sensing data, describe three differences between some different imagery types, namely NAIP, Landsat 8, and MODIS. And we're going to focus on how they're collected, how frequently they're collected, and the spatial and spectral resolutions and how they differ. And then finally, we're going to describe spatial and temporal trade-offs between data collected from a satellite versus an airplane. And so we're all set up because we have a code space. Let's get into some of the higher level descriptions of multispectral data. So in last week, we really focused on LiDAR, which is an instrument. It's an active remote sensing instrument. It can be attached to airplanes, drones, satellites, but it's fundamentally different from multispectral data in that the LiDAR emits energy actively rather than collecting information about light energy from the sun. And so this week, we're going to work with multispectral imagery, and it's a passive remote sensing type. So that means that we're measuring light energy from an existing source. We're not emitting any new light radiation from the sensor. It's just kind of capturing the light reflected from the sun. So you can see in this diagram here, there's a remote sensing system in clip art mode, which measures energy that's naturally available, and it's called a passive sensor. So you can see how the sun is shining its beautiful light on the Earth, and then this light is reflecting via these arrows up to the sensor on this satellite. This is in contrast to the active sensor on the right, which you see how there's no sun in this diagram. So it's implying that the sensor is emitting its own source of light, and then in turn capturing the reflected light back and measuring that. So to better understand multispectral remote sensing, we're going to learn some of the basics and watch a couple more videos that are a little cheesy but informative as well. And so the electromagnetic spectrum is composed of a range of different wavelengths or colors of light energy. A spectral remote sensing instrument collects light energy within specific regions of the spectrum. And each region in the spectrum is referred to as a band, hence multiband, multispectral imagery. And so now let's watch a few videos. And so we're going to watch the full overview in this first one, and then we're just going to watch the first 8 minutes of the second one. So let's get into it.
If you've ever used a camera, then you know something about spectral remote sensing. Spectral related to the electromagnetic spectrum, which includes light that is both visible and invisible to human eyes, and remote sensing, which involves measuring the properties of objects without directly touching them. The typical camera that you use measures and records visible light that objects like trees and rock reflect. This light might come from the sun, but it also might come from other sources, like light bulbs. While we often use cameras to take selfies and silly pictures of our furry friends, scientists use high-powered cameras called imaging spectrometers to measure changes in things that impact our environment, like water quality or vegetation cover and health. Imaging spectrometers mounted on airplanes and satellites help us create maps, like this vegetation cover map for the entire United States. But how exactly do scientists measure changes to our environment using reflected light energy? To answer this question, let's have a look at the electromagnetic spectrum, which is composed of thousands of wavelengths of energy. Visible light, what we see with our eyes, is contained in the blue, green, and red portions of the spectrum. The rest of the spectrum is not visible to human eyes, but can be detected and recorded by sophisticated camera-like sensors called imaging spectrometers. Now, there are thousands of wavelengths to record in the electromagnetic spectrum. To deal with all these wavelengths, imaging spectrometers divide the spectrum into groups of wavelengths called bands. For example, a band in the near-infrared region of the spectrum could include energy from 800 to 850 nanometers. This band is useful to map healthy vegetation. The width and number of bands is what we call the spectral resolution of an image. Higher spectral resolution means more bands that are spectrally more narrow. Lower spectral resolution means fewer bands, each of which covers more of the spectrum. Now, imaging spectrometers measure reflected light energy. You see, different objects reflect, absorb, and transmit light differently, depending on their chemical and structural characteristics. For example, plant leaves are green because they reflect more green light than blue or red light. On the other hand, Fido the dog reflects more light in the red portion of the spectrum because of the chemical and structural makeup of his fur. If Fido's chemical and structural makeup was the same as a plant's, then he would look green. Now, when you point your camera towards your favorite canine doing something silly, the camera records the amount of light reflected from the dog and its surroundings in the visible, or red, green, and blue bands of the electromagnetic spectrum. The camera creates what's called an RGB image, which is composed of millions of pixels. Each pixel in the image contains a value representing the amount of red, green, and blue light reflected. We can break the image out into its red, green, and blue bands too. Here's the red band on its own. Brighter pixels mean that more light was reflected by objects in the image and recorded by the camera in the red part of the electromagnetic spectrum. The darker parts are areas where less light was recorded. When we combine the red, green, and blue bands together, we get an image that looks similar to what we see through the camera lens. We can plot the amount of red, green, and blue light recorded in each pixel to create what's called a spectral signature. In this signature, the amount of energy reflected in a particular wavelength is shown on the y-axis, and the full range of wavelengths that were measured by the camera, in this case blue, green, and red, is on the x-axis. The spectral signature for Fido is quite different from the spectral signature for a plant. This makes them appear visually different to our eyes too. Differences in spectral signatures can help scientists identify different types of surfaces and objects within images. Most cameras record light in the visible or red, green, and blue bands. However, plants, dogs, and other objects on the earth also reflect light that we can't see with our eyes. For example, plants reflect up to 60% more light in the near infrared portion of the electromagnetic spectrum than they do in the green portion of the spectrum. This is why differences in reflected light in the near infrared portion of the spectrum are important for mapping vegetation on the ground. To measure these differences in the non-visible portion of the spectrum, we use imaging spectrometers, which record light in both the visible and non-visible parts of the spectrum. Imaging spectrometers produce what are called multi- and hyperspectral remote sensing data. Multi meaning many bands, more than 3, and hyper meaning up to hundreds of bands, collected at very high spectral resolution. We use these multi- and hyperspectral remote sensing datasets to measure light energy reflected from objects on the Earth's surface, and to estimate many physical and chemical properties of objects that we wouldn't see with our own eyes. We then use those measurements to classify what's on the ground. For example, pixels that have a spectral signature with a lot of near-infrared light energy are often vegetation. To review, different objects reflect, absorb, and transmit both visible light and light energy that we can't see differently. Imaging spectrometers record the amount of light that these objects reflect. The amount of light energy reflected by an object throughout the electromagnetic spectrum is called its spectral signature, which is driven by the physical structure and chemical makeup of the object. We can use that signature to identify different objects in both a photograph and across the Earth's surface. And that, my friends, is how we use reflected light energy to both map what's on the ground and measure changes in our environment.
Very cool. Before we jump into the next video, are there any questions from this overview about spectral? Okay. Let's jump in and watch this next video for about 8 minutes, and then we'll continue on.
I want to start by just, something everybody's familiar with, just a typical RGB digital camera that we all use. So normally this type of sensor takes information in 3 bands, red, green, and blue, which come from this portion of the electromagnetic spectrum. Of course, all the time the sun is putting down energy from this entire spectrum. We've designed these cameras to capture information in that little portion. Anyone know why we grab the information from this portion as opposed to any other section of the spectrum? We can see it. We want our pictures. It's not a trick question. We want the pictures that we take with the camera to look like what we see with our eyes, right? And so out of all that spectrum, we take the information from the visible portion. What makes the visible portion special? You guys remember atmospheric windows, remote sensing course? So this is same spectrum that we see here on the x-axis. And then we have percent reflectance on the y-axis. So what we can see here is that there's some portions of the spectrum that aren't able to transmit through the atmosphere. These regions that you kind of see here in the blue are very transmissive through our atmosphere. And so the visible spectrum lands right here in this nice thick part of that atmospheric window. So we got all kinds of this visible energy coming down. And so essentially this is why our eyes have evolved to see this portion of the spectrum, because there's a lot of that energy available because it was able to transmit through the atmosphere. So we can look at the actual wavelengths for each portion or different portions of the visible spectrum. So I've got red, green, and blue up there. So red, for example, goes between 620 to 750 nanometers. So we have in our digital cameras that take this information, a sensor that, you know, figures out the signal strength for that portion of the spectrum. And it does that in the red, green, blue bands. In each one of these, the dark areas represent where we didn't get a lot of signal. Lighter areas represent where we got more signal. So this is an image from San Joaquin Experimental Range, which is one of our sites in D17. So then what we can do, we can take the computer and we can color the red band with red, green band with green, blue band with blue. That's great. Take those three bands, if we color them, stack them up, and we get an RGB image, which is our true color image, right? So what's important to realize though is that we don't have to do that. Instead of making an RGB image, well, I could take the information I got from the blue band, color that red, here, information from the green band, color that green, and the information I got from the red band and color that blue. And I can get this. Doesn't look like much, right? Doesn't look like our eyes would see it. But with this and with the ability to separate these bands, we have the freedom to do this if we want. Same thing, I can make another false color image like this, where I've put the different bands and colored them differently. Of course, normally we don't want to do that because we want to see the image like we want to see, like our eyes see it. So we got a true color image. We're good, right? That's all we want. We see it, an image like our eyes see it. But there's this whole other portion of the electromagnetic spectrum that had tons of other information in it. So we actually want to build detectors that are able to see these other portions of the spectrum. And so I've got examples of Landsat 8, Landsat 7 here, which are two satellites. You can see that they're collecting information, these other portions of the spectrum. Here's our visible portion way down here. And as we move up, near infrared, middle infrared up here. So we can actually look at all the different bands and where they're collecting. Again, here's this visible portion, Landsat 8, and here near infrared, shortwave infrared. Is anyone here from Colorado? Recognize here? So this is Fort Collins, Colorado, just north of here. This was the first image that was ever taken with Landsat 8. And so if we look at, say, a reflectance curve from Landsat 8, which is all the values from all the different bands, we can get something like this for different features. So I think we have forest here. So if we look at the visible, it's kind of here, and then this goes into the near infrared and mid infrared. So we can get values of the reflectance across all the different bands that Landsat takes. So you get these curves here, but since there's so few bands in Landsat 8, because they're so wide, you sort of get these very sharp breaks in them. And so And down here in Landsat 8, we have the panchromatic band, which is, if you look at its band limits, it actually contains most of the visible portion, and it's done at a little bit of a higher spatial resolution. So did anyone remember from the remote sensing classes or experience why we were able to get a better spatial resolution, 15 meters, as opposed to lower spatial resolution on the other bands, 30 meters? Sorry? Yeah, so there is a little bit less in the visible, but this actually covers the same values as these here. Yes.
Get more radiance around that, so you get more information into the hyperspectral detector.
Yeah, exactly. That's essentially what's happening. So, I mean, if you can think about, say, a CCD array detector, you can make a whole bunch of different elements that detect the energy in each of those individual bands. But the smaller you make them, the less energy that they're going to be able to detect, right? And so if you want to get a good signal, good strong signal, remember all these are going to have a little bit of noise in them. So if you want to get a good strong signal, you have two choices. You can make your detector elements bigger, or you can accept more energy from a larger portion of the spectrum, right? And so if we go back to the Landsat, see, these are a little bit narrower. Say blue, 433 to 453. This goes all the way from 500 to 680. So we're collecting a larger portion of that spectrum. It's more energy, gives us the ability to have smaller detector elements, get a better spatial resolution.
Okay, so that first 8 minutes definitely covered a wide variety of topics. Towards the end, we're getting a little more into the weeds of sensor design and limitations around that. So if it was a little kind of sounded like noise, that's fine. The main kind of focus there is that I guess I'd want you to take from those first two videos. The human eye is kind of able to detect a lot of specific light reflected from our environment, but there's so much other information, rich information present that we're just not able to see and visualize. But scientists and engineers are able to build these awesome sensors. Some are passive, some are active, that are, or I guess we're specifically talking about passive here, and they're reflecting all this rich information. And you can build different kinds of sensors to either be more focused on really high resolution in terms of being able to see smaller features on the ground versus being able to collect more rich light information, so varied channels of light information. And we'll kind of, over the rest of today, kind of dive deeper into what that actually means practically, and along the way, some more theory as well. So are there any questions after those first two videos, or can we proceed? All right, and feel free to ask in chat. I'm keeping an eye on that as well. So key attributes of spectral remote sensing data. Space versus airborne data. So remote sensing data can be collected from the ground, the air, like using airplanes or helicopters, or from space on satellites. So you can imagine the data that are collected from space are often a lower spatial resolution than data collected from an airplane. The trade-off, however, is data collected from a satellite often offers better up to global coverage. And so there's this trade-off between being able to cover more area versus getting finer grained information. And so even like when you're taking a photo with your phone of something, if it's really far away and you try to zoom in, there's only so much zoom you can get with your pixels before it's just kind of blurry, and you can kind of see what's going on, but not really. And so that's when you might need a more specialized camera to look further, or like a lens that enables you to zoom in more. And so that's where, or you could just walk closer to the thing that you're trying to take a photo of. And so that's kind of the trade-off between being zoomed out in space, you're really far, you might need specialized zoom, or you can't zoom in past a certain point, versus if you're on a helicopter or an airplane, you're a lot closer to things. So it's just easier to see even with less intense like lenses and stuff. And so let's kind of zoom into a specific example of a satellite and an airborne observation platform. So Landsat 8 has a 16-day repeat cycle for the entire planet. And so you can find a new image for an area every 16 days. That's pretty cool, but it's also zoomed out. And so and also it takes a lot of time and financial resources. I mean, satellites are expensive, but also if you wanted to replicate this with airborne data, it would be cost prohibitive. And so, and by airborne, we mean collected by airplanes. It's just you'd have to be flying so many airplanes continuously collecting this data that it's just realistically not feasible. And so satellites are that nice trade-off, I guess. It's a compromise at the end of the day. And so one of the things with airborne data as well, you might not find data for the time you need. For example, with NAIP, you only get a new data set every 2 to 4 years. This has changed. I mean, NAIP is free, but there's data options now due to companies like Planet, where you're able to purchase really high resolution imagery that's happening often, similar to like a Landsat, if not faster frequency. And so things are changing rapidly, but traditionally it's been very challenging to get frequent high resolution data. NAIP is case in point. And so here we can see the difference between some data that's been collected. So this is a spaceborne digital surface model from a satellite, a traditional photogrammetry digital surface model from airplanes, and airborne LiDAR digital surface model from an airplane. And you can see the contrasting crispness of the imagery, largely due to the different spatial resolution. So the spaceborne DSM is 5-meter resolution. So you can kind of tell, yeah, it's like a city of some kind, but it kind of gets a little murky if you want to zoom in beyond a certain kind of view. Traditional photogrammetry DSM kind of is definitely an improvement, as you can see, but the airborne LiDAR DSM is kind of a tier above with the 0.5-meter resolution in terms of being able to see what is going on in the area and extract useful insights. However, you can't really collect airborne LiDAR data that often, maybe every few years. And so if you're trying to track change over time, like some maybe deforestation or urbanization in areas, using a spaceborne system, despite the reduced spatial resolution, will really better suit your needs. So let's now talk about bands and wavelengths. So when talking about spectral data, you need to understand electromagnetic spectrum and image bands. Spectral remote sensing data are collected by powerful camera-like instruments known as imaging spectrometers, and these collect reflected light energy in bands. So a band represents a segment of the EM spectrum. You can think of it as a bin of one type of light, or like a channel, like a radio station or a TV station, just red light. So for example, the wavelength values between 800 nanometers and 850 nanometers might be one band captured by an imaging spectrometer. So these sensors collect reflected light within a pixel area on the ground. And so since these sensors collect many different types of light, for each pixel, the amount of light energy for each type of light or band will be recorded. So you have like a stack of values for each area on the ground. So for a camera, that would equate to red, green, and blue light for each pixel. In a multispectral sensor, you might have 7 or more. In a hyperspectral sensor, you might have 100 layers of data. We're not going to dive into hyperspectral too much this semester, but it's a cool area of remote sensing that kind of takes multispectral to another level in terms of amount of data, but there's also trade-offs with working with such large data, like we've previously discussed with LiDAR systems in full spectrum versus kind of the discrete return data models. So when you work with multispectral data, the band information is reported as the center wavelength value. And this will all be kind of in the metadata of the raster files that we're using in Python. So we'll see some of that later today when we're kind of diving in with Rio X-ray and stuff. But the value represents the center point value of the wavelengths represented in that band. So a band spanning 800 to 850, the center would be 825. And then here you can see some examples of the electromagnetic spectrum, the specific visible light region where our eyes are able to process light and detect it. And then here is really zoomed into one specific band between 750 and 800, kind of this end section right here. So now let's talk about spatial and spectral resolution. So for spectral resolution, for a data set that has more than one band, it refers to the width of each band in the data set. So in the image above, a band was defined as spanning 800 to 810 nanometers. So the spectral width or the spectral resolution is 10 nanometers. So it's just the difference of the two values of the lower bound and the upper bound. And to see an example of this, we can check out the widths of the Landsat sensors. And so this page has been moved, so they need to update their links. But here we can see the wavelength. This is a 10 nanometer band, another 10 nanometer, 10 nanometer. This one is 3 nanometers, or no, 30 nanometers. Math is hard. You can see here different band or spectral resolutions for the bands. Not all sensors collect information within bands of uniform widths. So you can see that in that Landsat example that I just closed, there were some bands that didn't follow 10 nanometer width, some were 30, some were different. So it kind of just varies. You just need to check in the metadata of your data. So now we talked about spectral resolution. Let's talk about spatial resolution more directly. We kind of briefly discussed it with the DSM example above, but the spatial resolution of a raster represents the area on the ground that each pixel covers. So if you have smaller pixels in a raster, the data will appear more detailed, like the 0.5 meter resolution image in the DSM. If you have larger pixels in the raster, the data will appear more coarse or fuzzy, like the 5 meter imagery from the Spaceborne sensor. So if high resolution data shows you more about what's happening on the Earth's surface, why wouldn't you always just collect high resolution data, i.e. smaller pixels? So if you recall, you learned about raster spatial resolution when you worked with LiDAR elevation data, and the same resolution concepts apply to multispectral data. So the increased richness in information with the higher resolution really does come at a cost of having to store more data, which is actually expensive. Like storing information in a computer somewhere online costs money. It's not just free. I mean, it's free when you're using something like Google Drive for personal use and Dropbox, but if you're working at like a company and you just store data online somewhere, they are paying for that. So the more data you have to store, the more expensive it is. If you have to process it and analyze it with some kind of algorithms, it just costs more because there's more numbers to do math with. So it becomes an increasingly more expensive operation. And so that's one of the main trade-offs of dipping into the waters of high resolution data, whether it's LiDAR, multispectral or hyperspectral. It's just increased cost of computing and storage. So what is multispectral imagery? I'll get off my soapbox of compute expenses. But I mean, it's true. I'll stand on my soapbox a little longer, but companies can be spending tens, hundreds of thousands of dollars a month on compute costs in the cloud. And so I think that that's something that when I was in school, I didn't really hear about as much, but like there's a lot of money going around in the internet just for like being able to run things on computers and so or store things on computers like AWS. The government bulk stores tons of data on Amazon S3, and that's not free. You know what I mean? They're paying Amazon. And that happens at the city level too, or like even using Esri's data portal. That's not free. I think that municipal governments, as part of their contracts and stuff with Esri, are paying to be able to host that data and these portals. And so there's a lot of industry and money around the storage and accessibility of, not accessibility in terms of like accommodations, but accessibility in the sense of open data access. There's a lot of money in that. And so I just wanted to kind of call that out. So introduction to multiband raster data. So earlier in this course, we worked with raster data derived from LiDAR remote sensing instruments, namely the canopy height model, which was a pretty cool experience. These rasters consisted of one layer or band and contained height values derived from LiDAR data. So the digital surface model, the digital elevation model, and then we did some raster math and derived the canopy height model. So in this lesson, we're going to learn how to work with rasters containing multispectral imagery. And so these are going to be data stored in multiple bands or layers. And so we're going to use raster.io open again. And this will help us open multi-band raster data in Python. And we're going to use the stack function to help us import multi-band raster data. Likewise, we're able to plot true color imagery really easily using the EarthPy plot RGB function. And we'll get some experience with that today. Here you can see an example of the difference between a single band raster, like a digital elevation model, versus a multi-band raster, which is multiple layers sandwiched together. And so just to kind of further reinforce that we're already familiar with a lot of these concepts, just from a less scientific perspective, one of the most common, or probably the most common multispectral image that we all interact with is like a color image. So like a selfie, like the video described, or even just looking at stuff on Google Maps, or just any kind of rich media presented on like a streaming service or whatever, or an app for liking and viewing things. This is all color images with 3 bands of information: red, green, and blue. And so just wanted to call out that we're all already pretty accustomed to operating with multispectral imagery. We just don't really think about it that way. And it's cool because we're not limited to only thinking about it in the red, green, blue context. The second video was starting to call that out a little bit, where you're able to create false color composites that highlight different aspects or areas of the spectrum that this image is reflecting in. And we'll get a little experience with that this week, and then a lot more experience with it next week. So here you can see a multi-band image. A single band of it just looks like kind of the LiDAR height rasters we plotted previously in this course. But when you plot the 3 bands together, it appears much more kind of aligned with how we perceive reality with our eyes. This doesn't account for people with anomalies or abnormalities in their vision or color blindness or whatever, but I'm saying for like the general population, that's kind of how they perceive colors. And then you're able to plot bands separately, but together to really show how in certain regions of the spectrum or in certain bands, there's features in the image that are accentuated. And so this is kind of the precursor to next week where we're taking bands and doing kind of formulas to combine and stack them in different ways to specifically highlight certain phenomena that we're interested in, whether that's vegetation, buildings, water features, you name it. And like I had alluded to in the video briefly discussed, we're not limited to just red, green, blue composite imagery. A really common example of a band combination you'll see is swapping near infrared or swapping red for near infrared. And this really exaggerates the appearance of vegetation because even though we cannot perceive it with our human eyes, unless you're like some kind of cool superhuman, plants reflect a ton of near infrared radiation or light. We just can't see it. And so we can make cameras or sensors that capture that and then use it or I guess perceive it using computers. And so to me, computers are awesome. They really empower us to do so many things that would not be previously possible. This is one of them. I mean, you could do this with film in a way, but it's pain. Computers really empower these kind of analyses and stacking and recombining image data. There's also other types of multiband raster data. You might see time series of a region collecting the same bands over the same area over time. There's also hyperspectral imagery. We're not going to cover that this course, but it's pretty cool. Another thing, there's also kind of overlap. LiDAR is collected in one band predominantly, but I've also heard there's hyperspectral LiDAR. So it's emitting radiation in multiple bands and then collecting it. And so it's just like insane data. We're not going to touch that at all this semester, but something to look into if you're curious and like nerding out on data tech things. So now let's pivot to three kind of fundamental common data collection platforms that are used in a wide variety of remote sensing studies. NAIP is predominantly a US-based, or it's entirely a US-based data collection operation through the USDA, pretty sure. And it's collecting high resolution imagery of the continent, or yeah, the continental US, maybe Alaska too, I'm not exactly sure, but at a 1 meter spatial resolution. I believe a lot of this is used in support of agricultural decision making in the United States. Landsat is another US-based project, but this one is not on an airplane. Sorry if I didn't call it out previously, but NAIP is on an airplane. That's why it's only collected kind of once a year. Whereas Landsat 8 is on a spaceborne satellite, so it's able to do repeat data collection every 16 days, which is pretty cool. And in contrast to the high resolution or high spatial resolution of NAIP at 1 meters, Landsat is much coarser at 15 meters or 15 for the panchromatic band. And here we can see some of the kind of stats about the sensor, namely the bands that it's collecting in. This is in contrast to NAIP, which is just collecting red, green, blue imagery. Sometimes NAI or near infrared, but predominantly red, green, blue. So Landsat has a much larger variety of, or a diverse spectral content, and then it's much more frequently collected. And so despite the lower spatial resolution, it has some benefits that NAIP just cannot provide. And then finally, we have MODIS, which is zooming out even further. I don't know if MODIS, it might have started out with NASA, but I feel like it might be more of an international project at this point. I think Landsat as well is fairly collaborative across countries, but I could be wrong. The MODIS is a more OG satellite platform and it collects data at a 250, 500 meter, or 1,000 meter spatial resolution. So it's very coarse, but you can see there's 36 bands. And so it's much more rich in certain respects. And so there's limitations and trade-offs between these different platforms. Certain, like, you're not going to necessarily study a specific meadow in a valley using MODIS imagery, because it might just appear as a single pixel and there's nothing that you can discern. But if you're maybe tracking the entire sub-Saharan region of Africa, you might want to use something like MODIS just because it's more practical. And you're able to track a lot more in terms of spectral content. So this is another one of those kind of like teaser labs where there's not actually code. So let's create just some silliness here. Restart code space. It's because I was just lagging and not doing anything. So if you had that too, just restart your code space and then it'll just boot up in a second. It's because we were just reading and not actually coding. Once it's back, we'll just put a print statement in this notebook and then continue on with the next lesson. So let's just say, so we have to select a kernel. It has 3.10.13, perfect. And if you don't auto detect 3.10.13, just make sure you click the select kernel and then specify Python 3.10.13. So I'm just going to do print multispectral data. Sounds cool. We're going to learn more about it, and then maybe we'll be able to be more affirmative or steadfast in like saying multispectral data is cool. But right now it's too early to tell. So let's save this, commit the change to our repository, and then we'll continue on. Finish lesson 1, click that check, and then pull and push. It's cool. Just close that out. And then if we return to our repository and refresh the page, you'll see that now we have an additional notebook there. Awesome. So I'm going to close this one. I'm going to close that notebook. And now let's create a new notebook called rendering. So in this notebook, we're going to discuss how multispectral imagery is drawn on computers. So we already have the Python 3.10. Awesome. I'm going to open this lesson and then we'll get into it. So we're going to very briefly in this short little lesson describe the difference between additive and subtractive light models and explain how red, green, blue images are rendered in a computer monitor. So let's watch these 2 videos and then continue on.
We have red, green, and blue lights. Why are these shadows not red, green, and blue? We have our 3 lights, red and green and blue, shining on the board. It looks white. When I put the pencil in and cast shadows, the shadows are yellow, magenta in the middle, and cyan. To understand how that happens, we can turn off the lights one at a time so that only the red light shines on the board, making it red. Now when I cast a shadow, it's a dark shadow. It's the one place on the board where there is no red light. So we can think of the shadow as subtracting red light from the board in the position of the shadow.
Cool. And then let's hop into this next video.
What color are these chocolate candies? How about these ones? One white and one black? Nope. The white M&M can reflect any color of light, but the red M&M only reflects red. Blue makes it look black. Green makes it look black. Aqua makes it look black, but red, it reflects red light only. This red M&M is red because it reflects light, but as you could see, the white M&M could reflect any color. Dyes and paints are subtractive. They prevent light from being reflected. For example, red paint would prevent blue and green light from being reflected and only reflect red. Subtract. Mixing blue and yellow reflects less blue and less yellow, and no red. The result is green. If we mix the red and the blue together, we'll now get less red and less blue, and no yellow. The result is purple. The mixing of light is in no way similar. It's additive. When you mix red and blue lights, it adds light. This is a device used to mix the primary colors of light: red, blue, and green. If I mix red and blue, I get magenta, a type of pink. If I mix blue and green, I get cyan, an ocean blue. And if I mix green and red, I get yellow. Those are the secondary colors of light. The color wheel for light is not at all the same as the color wheel for paint. When you mix paint, for example, red and yellow, you get orange. Red and blue, violet. And blue and yellow, green. For light, red and blue mix to make magenta. Red and green, yellow. And green and blue mix to make cyan.
My brain hurts already. Okay. And then one more. So this video has no sound, but let's look as they zoom in and let's try to notice the pixels. Okay, so we know they're in Germany. We're a German-speaking country. So you can see all the pixels. It's fairly coarse screen compared to modern day touch screens. And you can see just if you zoom in, it's actually just combinations of red, green, and blue. There's no white. It's just zoomed out enough that we perceive it in such a way that it looks white. So that's kind of gnarly. So yeah, that's I think kind of the main point in this video. But this is another one of those kind of teaser labs. Let's just put another print statement that say print colors are weird, man. Feel free to put whatever print statement you want related to colors. So let's save this, commit our change to GitHub. I'll commit and sync. And we'll do finish lesson 2. Okay, and don't show again, because I don't want to see that again. Awesome, and then we can close this notebook. I like to double check that it got committed, and you'll see that we have one right there now. That's awesome. All right, getting through. Next, let's create a new notebook called NAIP. and we're going to learn how to use NAIP multiband remote sensing images in Python. So let me open Slab. Cool. So we're going to learn how to work with NAIP multiband raster data stored in TIFF format with raster IO. And that's kind of the high level what we're going to do. But more specifically, we're going to learn how to open red, green, blue imagery with 3 or 4 bands in Python with Rio X-Array. We're going to learn how to identify the number of bands stored in an image with Python. So like looking at the metadata. And then we're going to get some practice plotting various band composites using true color, RGB, or color infrared kind of composites. So we're going to need to download the data, which we'll do shortly using the EarthPy data get data method that we've used previously. So before we jump into the Python, let's do a quick overview of NAIP one more time. So the National Agricultural Imagery Program acquires aerial imagery during the agricultural growing seasons in the continental US. The primary goal of the NAIP program is to make digital orthophotography available to government agencies and the public within a year of acquisition. NAIP is administered by the USDA's Farm Service Agency through the Aerial Photography Field Office in Salt Lake City. This leaf-on imagery is used as a base layer for GIS programs in the Farm Service Agency's county service centers and is used to maintain the common land unit boundaries. So it's a pretty important data set in terms of the monitoring and inventorying of US farmland. And so this is used kind of at the intersection of environmental research and kind of land management and government. So NAIP is a great source of high resolution imagery across the US. It's often collected with just a red, green, and blue band. However, some flights include a near infrared band, which is very useful for quantifying vegetation cover and health. So you can download NAIP data from the Earth Explorer website, but we're using data provided by EarthPy just for the sake of ease and learning. But you're able to access a variety of data sets or collection years and locations around the US if you go to the USGS Earth Explorer website. So now we're going to pivot to Python, get our fingers warm with some imports, and get started. So before we import anything, we're going to need to install some libraries. Let's install Rio X-Array. Oops, got to spell it right. GeoPandas, EarthPy. I think that should be good. I think that's all we'll need. Okay. So you can see it's just installing things and we'll be good to go. So once that's successfully installed, let's import everything we'll need. So we'll start with OS, matplotlib, pyplot as PLT using import aliasing, import numpy as NP, import Rio X-Array as RXR, import, GeoPandas as GPD, import EarthPy as ET, EarthPy.plot as EP, import EarthPy.spatial as ES. So let's make sure all those imports work. Awesome, no errors. Now let's actually get the data, set our working directory, and specify some figure plotting parameters. So data equals et.data, get data, and we want to get the Cold Spring fire data set. And then in the same cell, let's also set the working directory using os.shadir. I don't know if that's the correct pronunciation, but that's what I've always called it. And we'll specify os.path.join, and then we'll pass in earthpy.io.home, and then earth analytics and data. So you see we got an error, and that's because there's no such data set as the Cold Spring fire. It's Cold Springs. Simple typo, no biggie. Happens all the time. I'm sure it'll happen again to me too. Awesome. We have the data saved and we set our working directory. Now finally, let's use pyplot to set the figure size and the axis title size. So we're not using Seaborn right now, we're using PLT directly. So there's lots of different ways to kind of set figure parameters, and we're learning another one this week. So figure dot fig size, and we want to set that to 10 by 10. If you remember in previous weeks, we've used PLT subplots, and we specified a fig size directly in there. This is another way to do that. Similarly, we'll do PLT RC params, axes.title size, and we'll specify this to be 20. Okay, and so now let's use Rio X-Array, specifically the Open Raster IO function, to open the multiband NIIP imagery. And let's not forget to mask out the fill values using the masked equals true parameter. So we'll start NAIP CSF path. CSF stands for Cold Springs Fire, in case you're wondering. OS path join Cold Springs Fire. NAIP M. Well, that's a nasty one. 3910505 NW 13-1 2015 0919. And we'll see if there's any typos shortly. Crop. And then M 3910505. This is definitely not best practice, but oh well, we're gonna type it out anyway. Oh no, living dangerously. We'll put it that way. Crop.tif. Okay, so we have our path. Now let's create a new variable and then read in our data into that variable. So we'll call it NAIP CSF equals RXR open raster IO NAIP CSF path, and then mask equals true. And then let's just see what it goes, or what it looks like when we output it. So no typos on my end, awesome. So we import a geotiff like we've done before, but notice that the shape of our resulting NumPy array is a little different. Previously, we had maybe one band, and then we'd kind of squeeze the data so that they would not have that extra layer. But notice now we have 4 bands of information. So that's kind of interesting to note. It looks a little different than before. So let's actually check the shape of our data set using the shape parameter. And we'll see that it's 4 layers by 2312 and 4377. So it's actually like a sandwich of information, a tasty delight of data. So we can start by plotting a single band, and we'll do that. And then we'll kind of go further and get some practice doing multi-band plots. So let's use AX or what is it called? Let's use the RxR ImShow utility. That's what it's called to plot some data. Big AX equals plt.subplots. And notice how we don't specify the fixed size because we've already hard coded that at the top using the RC params. So then I misspoke. It's not an RxR tool. It's a PLT utility, the ImShow. So we'll invoke ImShow on the NAIP CSF data. And we just want to put in the first band. So band 0, because Python counting starts at 0. And then let's set the color map to be grays, but in reverse. And then let's set the title to be NAIP RGB imagery and 1 red. New line, Cold Springs, fire, scar. Let's turn off the axis and then we'll show it. And so you can see here we're plotting band 1, which is the red band, and we're seeing our data, which is cool. But let's actually learn a shorthand way of doing that. We don't have to go through the ImShow. We can actually use EarthPy directly and the plot bands utility. So let's do EP dot plot bands. Oops. Let me copy this. EP dot plot. Actually, no, I don't even have to do that. EP dot plot bands. NAIP CSF 0. I'm so used to typing CSV instead of CSF. Title equals NAIP RGB imagery and 1 red, Cold Springs fire scar, C bar equals false. And then let's do a PLT show. Nice. Essentially the same figure with 2 lines versus 1, 2, 3, 4, 5 lines. Pretty nice. Now let's inspect a single band element of our raster. Let's check that out. NAIP CSF dot band. What does that look like? So it's just an array, and doesn't tell us too much, but it kind of gives us an idea. But we'll note that there are 4 bands in this one, which, yeah, we've already made that clear. And then for NAIP data, because that's what this is, we can know that this is red, green, blue, and near infrared data. Previously, we just had single layer bands or single layer data sets. So let's print the max and the min of our data. See what that kind of outputs, because I don't know what it'll say because we have 4 layers. So is it just going to be the min across all layers? A single one? We'll find out. So NAIP CSF min 17. Okay. Interesting. And then if we do, so the lowest value is 17. What about the max? 242. Okay. So this raster contains values between 0 and 255. So these values represent degrees of brightness associated with the image band. In the case of an RGB image, band 1 is red band. Larger numbers towards 255 represent pixels with more red in them, a strong red reflection. Smaller numbers towards 0 represent pixels with less red in them, so less red was reflected. So now we're getting a little closer to plotting multi-band imagery. But before we do that, let's skip over some of this. Yeah, I don't think we need to plot the green band because we already plotted a specific band. This is basically just showing a different one, so we can skip over that. We don't need to spend too much time talking about rasters and NumPy arrays because we did this last week. We just wanted to call that out. Let's actually plot all the bands together. So we'll do that like this. Let's create a list called titles, and we'll set it to red band, or I'm not going to write band every time because I'm lazy. So we'll just say green, blue, NIR. And then let's plot all those bands. EP.plot bands, NAIP CSF, big size equals, we're going to override what we set before and specify a different fig size. We want 2 columns. We want title to be titles, and we want the color bar off. And then let's do a PLT show, and let's fix the typo there. And now we should be fine. Cool. If you really like, let's just kind of side quest real quick. For title in titles, title equals title plus band. Let's see if that changes our figure. Or if I'm being silly. No, it's not. Okay, yeah, it didn't update place. Okay, that's fine. I know there's a way to do this. I just haven't done it in a second. Titles plus. Let's try that. No, okay, yeah, it doesn't like that. Okay. There's a way to iterate through. We don't have to do that right now. It's chill. I was just trying to be a little tricky, but it's not that important. So now let's plot RGB data in Python. We're going to use the EarthPy function called plot RGB and get right to it. It's pretty simple. Plot RGB, NAIP, CSF, and we want to pass in the values, so the NumPy array, and we want to set RGB equals to 0, 1, 2, so it knows which bands. I'm going to copy this typo that I constantly do now because I'm used to writing CSV instead of CSF. And then let's set the title equals to RGB composite image. Sorry if you hear my stomach growling, I'm a little hungry. PLT.show. Awesome. We plotted our first RGB composite image of the NAIP data with Python. Pat yourselves on the back. That's pretty cool. Let's plot a color infrared composite now. Very similar to what we just did. So similar, in fact, that I'm going to copy paste it and just do some minor tweaks because I'm a little lazy. So let's change the title to CIR NAIP image or CIR composites. How about that? We'll keep now let's change the RGB from 0, 1, 2 to 3, 0, 1. And now you'll notice that vegetation is all red. And so we're kind of plotting that in the red band, the NIR data in the red band instead of red. Cool. Let's also follow some of these optional challenges real quick. Let's make sense of a single band image. So let's plot all the bands in the NAIP image using Python, following the code examples above. It's basically given to us already, so I'm just going to copy paste that example so we can quickly move on. So we're essentially just plotting 3 bands of data, namely what we're plotting in this here. And so we can see the difference in how the data is being portrayed across bands. Do you notice a difference in brightness between the 3 images? This one seems very bright compared to all the others, whereas these have much more dark areas of contrast where there's less reflectance. So another topic that we'll briefly discuss is image stretch to increase contrast. The above image looks pretty good. And we can also explore whether applying a stretch to the image helps improve clarity and contrast. So you notice here there's an example of a fairly dark image where it's a little hard to discern elements on the ground. Applying a stretch really helps an analyst's ability or even an algorithm's ability to parse the different features on the landscape. So you can also see a washed out image. You can stretch to kind of better reflect across a variety of values. And so in our example here, this is one such image that could possibly benefit from some stretching. So let's use a package to contrast stretch each band in our data, namely the SK image package. So we're going to need to install that real quick, which is cool. But let's do that briefly. Ooh, so they actually built a stretch feature into EarthPy, so we don't even have to install SK image. Nice. So let's actually do that real quick. So we'll do band indices equals 0, 1, 2. So let's apply a stretch using the EarthPy plot RGB function. So there's a stretch option built in, which is pretty nice. So EP plot RGB, and then we'll do NAIP CSF dot values RGB equals band indices. Then we want to say title equals RGB NAIP image stretch applied. And let's say we don't need to apply a fig size because we just have one already. Let's do a stretch equals true. And let's do a PLT show. And so you'll notice now that we're plotting RGB image with the stretch applied to increase contrast. I'm going to do a very similar one here with no stretch so that we can kind of quickly toggle back and see how different they are. Notice here it's a little darker and kind of muddled in a way in some of these regions, whereas applying the stretch really enhances the contrast between the vegetated, slightly less vegetated, and bare regions. Visually, it may or may not be what you want to plot to the end user, but it does help with increasing contrast. And then to close out this lesson, let's plot a multi-band raster histogram so that we can kind of pick band values a different way. So let's specify some colors. We'll do red, green, blue, and black. K is the shortcut for black. And then we'll do titles, red, green, blue, NIR. Now let's plot a histogram using earthply, and we'll do NAIP CSF dot values. Colors equals colors. Title equals titles. Columns equals 2. PLT dot show. So you can see we have our blue, near infrared, red, and green. And you can see how there's a spike in, I'd say, blue, near infrared, and green in the kind of lower part of the histogram. Whereas for near infrared, it's kind of more muted in the beginning, and it actually bumps up the higher values. So it's a little different. You can even just see across the bands how the landscape responds. So next, let's save our changes to this notebook and continue on. So I'm going to now commit to our repository. Finish lesson 3. So we're 30% done with today's lab. Cool. Let's close that up. Return back here. Let's double check that everything looks good. And it does. So let's push on. So now we're gonna get NAIP remote sensing data from the Earth Explorer website. So let's create another notebook called get naip.ipynb. Let's open that. And then let's push forward with this. So on this page, we're going to review how to grab NAIP data from Earth Explorer website. It's a data portal run by the USGS, and we can find many types of remote sensing and other data for the US and in some cases the globe. So sometimes it could take a long time to download this data, so just be patient. So the high-level steps are from downloading Landsat data from Earth Explorer are define your study area, so your area of interest, kind of what we've been doing previously. For this week, that would be the boundary of the Cold Springs fire extent. We could also type in XY vertices for each corner, but you can also upload a zipped shapefile that contains your boundary instead. So be sure to use a square or rectangular extent polygon. If you have too many vertices in your extent polygon, the website will get angry at you. You can also kind of click on it, but the file that you want to upload is this file here, located in the data Cold Springs Fire vector layers directory, namely the fire boundary box shape.zip. Then we're going to want to create an account on Earth Explorer if you don't already have one, upload your shapefile extent, and then you can search for data available. We're not going to walk through that live in class, so that's more of a like do it later kind of thing, just because it can take some time, and I'd rather just not focus on the Earth Explorer side of things. But if you're running into any issues with that, don't hesitate to reach out to either your classmates or to me. And then once you upload your kind of study extent and select a date range, you can define the data you want to download. So we specifically want the NAIP GeoTIFF, but you'll see a variety of options that are available, including aerial photos, space-acquired photography, high-res orthoimagery, and others. So make sure you select NAIP GeoTIFF. Click on results and then download your data. So once you've downloaded your data, I'd encourage you to explore it a bit, whether that's using something like ArcGIS Pro, ArcGIS Online, QGIS, Python, R, whatever you prefer. But I'd say maybe just tinker with it a little bit. and get some experience. So let's actually do a print statement. We'll do this after class. We can save our changes and then commit to our repository. Finish lesson 4. Awesome. We can double check that everything worked correctly, and it did. Let's push on. And then there were 4. Okay, let's get it. So now we're going to work with Landsat remote sensing data in Python. Let's create a new notebook called landsat.ipynb. Open that. And then let's navigate here. So in this lesson, we're going to learn how to work with Landsat multiband raster data, kind of continuing what we've been doing. And specifically, we're going to create subsetted lists of file names using glob to kind of handle multiple bands that have similar names, but maybe are a slightly different label. So like band blah, blah, blah 1, band blah, blah, blah 2, and how to work on multiple files with similar names. We're going to create a raster stack from that list. And then we're going to learn how to crop rasters and plot band combinations. So let's jump in. So we previously learned how to import multiband image in Python with Rio Xarray. We also used pyplot-imshow. We didn't calculate NDVI yet, but we're going to do that next week. But all the bands were stored in a single TIFF. Sometimes when you download data, you get individual bands rather than a single file with everything together. And so in this chapter, we're going to learn how to work with Landsat data, which it's such a data set that we have individual TIFF files that we're going to need to grab and smush together to do things with. So let's get into it. So here's a high-level overview of Landsat. I have a feeling that you've all kind of heard of it previously, even before this class, and so we're not going to spend too much time, but this is just a OG like satellite families starting in the 70s all through today, and there's just multiple generations of this sensor satellite platform that are collecting data, so for the last 40 plus years. So the data are spectral and collected using a platform mounted on a satellite in space that orbits Earth. So below are the spectral bands and associated resolutions of the first 9 bands of Landsat 8. Excuse me. There's additional bands additional bands that are collected, but they're not distributed in specific surface reflectance product, namely the panchromatic band. So that's fine, and the cirrus cloud band. So it's just missing a few of the data sets that are collected, but we don't really need those for the purposes of today. And when working with Landsat, it's important to understand the metadata and the file naming convention. We've dove into metadata a few times already in this class on different data sets, but it's important. We're going to keep doing it. And so the metadata will tell us how the data was processed, where it's from, and how they're structured. And for Landsat data, the file names will often tell us the sensor that collected the data, the date where they're collected, and more. Specifically for Landsat, it'll tell you where they're collected and processed, what sensor was used, what satellite was used, and more information. So here is an example for Landsat. We have the Landsat sensor. The C stands for OLI TIRS combined. Operational land imager, I forgot what the TRS stands for. 08 stands for Landsat 8, not 7. So if it was a Landsat 7 dataset, it would be an LC07 or something similar. The next 6 digits represent the path and row of the scene. So that would be this 034032 that references where it is on the planet. And then we have the date. So this was collected in 2016 on July 23rd. Finally, we have the more information about when the data were last processed. You can learn more about that in this link here, but this is just kind of even more metadata. So something in 2018 and February 14th, something likely occurred. So let's import some Landsat data. I'm gonna go back to Python. Let's import some libraries and get into it. Import OS from glob, import glob, import matplotlib dot pyplot as plt, import numpy as np, import geopandas as gpd, import xarray as rxr, import xarray as xr, import Rio xarray as rxr, import earthpy as et, import earthpy.spatial as es, import earthpy.plot as ep. Okay. Nice. We have the libraries loaded in. We've already downloaded the Cold Springs Fire data. So instead of downloading it again, I'm just going to set our working directory and then we'll go from there. So I'll do os chadir, os path join, etio home, earth analytics data. Okay, now let's get a list of all the pre-crop data and sort it. So to start, that means we'll create a path to our data. So let's just use os path join like we've been doing previously. So Landsat post fire path equals os path join Cold Springs Fire Landsat collect. This super long name that I'm just going to copy paste. And crop. Next, let's generate a list of the TIFF files. So post fire paths equals glob. Actually, hold on. Before I do that, let's just let's see this step by step. So we have this variable now. What happens when we have so we have this path here. Can we do how does one do that in Python? I forgot. ls. Should I say how do we list files in a directory with Python? So you can do that using the listdir function. os listdir. So let's try that. os.listdir. So you can see we have a bunch of TIFF files. So without specifying any of them, we're just going to kind of grab them based off of this base path here, the crop. And so let's generate a list of the files. So we'll do post fire paths equals glob os path join, and then we want to pass in Landsat post fire path, and then we're putting in this asterisk which stands for wildcard. So basically anything before the word banned we're okay with, or after, and then TIFF. So we're looking for something that has the word banned in it. And so you can see here, that'll be these first 6 or 1, 2, 3, 4, 5, 6 layers. and then this one right here. So 7 layers total, whereas we're not gonna then be filtering for aerosol, pixel QA, or RadSat QA. So let's see what this looks like when we output it. And so now you'll notice that there's a subset of the files contained in this directory. It's only those that match this pattern where they have the word band somewhere and it's a TIFF file, which is cool. So we're able to filter a large folder for just specific files. And this is a pretty useful operation even outside of remote sensing kind of things. So now let's sort the data to ensure that they're in the correct order. So I'll do that like this. And then we'll output it again. But we can just visually inspect. These are not in the correct order. You can see here how that's band 2, 5, 3, 7, 1, 6, 4. Let's see if it actually outputs it in the correct numerical order that we want. And then if we zoom to the right, you'll notice band 1, 2, 3, 4, 5, 6, 7. So it's sorted for us. Awesome. So let's open a single band from our Landsat scene and use the squeeze method to ensure that our output X-ray object only has 2 dimensions instead of 3, like we did last week. And then we'll plot it really quickly. So we can do that like this. Band 1 equals RXR, open raster IO, post fire paths, 0, first one. Let's say masked equals true. And we'll say dot squeeze. Let's do a band 1 shape. Perfect. Now let's plot it really quickly. Equals PLT subplots. Band 1 plot. Dot imshow. AX equals AX. CMAP equals grays. R reversed. And then let's turn off the axis. AX dot set axis off. AX dot set title. Plot of band 1. PLT dot show. Awesome. Cool. Now let's use this function that they created for us. They being the authors of this textbook, that opens a single TIFF file and returns an X-array object. We're going to build this function out to process and clean our Landsat data in the following lessons. So to start, let's replicate this function. We're going to say define, open, clean bands, and the input is a band path. So it returns RXR open raster IO band path. So the generic path of whatever band we put in. Masked equals true. Dot squeeze. So this time we're kind of saving ourselves a little time. We don't have to futz around with typing out open raster IO each time. So now let's take each band that we open, stack it into a new single output array. This is only efficient if we want to process all the bands in our data, and given the size of Landsat data, you probably won't need all the bands. And so just wanted to call that out, that don't necessarily do this. This is more of like a learning example to use all the bands, because realistically, you're not going to necessarily need all the bands. So all bands equals an empty list. So for I, which is the integer-based index position. So for I, a band in enumerate post-fire paths. So we're going to be looping through the list of post-fire paths. All bands dot append. So we want to add something to this empty list of all bands. Namely, we're going to add open clean bands, a band. So we're calling our open clean bands function and passing it to each of the bands in our post-fire paths, excuse me. And then after we do that, we're going to assign a band number to the new X array object. And we'll do that like this. All bands I band equals I plus 1. Cool. And now let's optionally turn the list of bands into a single X array object. But before we do that, let's output all bands and just see what it looks like. So you can see here, it's just a massive list of X array things, X array data arrays. So we can then squish this into a single X array object as such using the concat method. So we'll do Landsat post fire XR equals xr.concat all bands on the dimension band. And then let's output this new object. And you'll see it's a single data array now with 7 bands and an extent. Very cool. Let us continue. Let's plot these data. All right. Landsat postfire XR dot mshow call equals band call wrap equals 3 and then cmap equals grays r, and we'll do a plt.show. Got an error, so I got to do a plot here. I forgot to put that in. And now we're good. Cool. So we're plotting all 7 bands at once. Very nice. Now let's plot an RGB image from our data. You'll see it's very similar to what we were doing previously. We'll do an EP plot RGB. We're going to pass in the Landsat postfire XR values. We're going to specify the bands to plot. Those are going to be 3, 2, 1. And then we're going to put in a title. RGB composite image. And then let's do a plt.show. Cool. And then notice how the image looks dark. We can actually apply a stretch to the image like we did with the NAIP. We're going to use the stretch argument built in EarthPy and the str clip argument that allows us to specify how much of the tails of the data to clip off. The larger the number, the more of the data will be stretched or brightened. So let's copy paste this and then just add in a little bit more for the stretching. So here, let's change the title RGB image, composite image, linear stretch. And then let's pass in stretch equals true. Gotta spell it right. Bang. And then str clip equals 1. Let's see what happens. So I spelled something wrong. What do we get? Okay. I'm missing something. Okay. One title stretch. That's what I have an erroneous quote. So now you'll notice that we've applied a composite linear stretch and we're kind of able to discern a little more in the image, which is nice. Let's try an adjustment of the linear stretch. So instead of having an STR clip of 1, let's do an STR clip of 4 and see how that affects the image. And you'll notice how it's really kind of just further enhancing the differences, at least to my eyes, with some of the green in the background and then this purple kind of indigo color against the background. Like we did previously, we can plot raster pixel histograms of our kind of stacked data array. So let's do that quickly. We'll do band titles, a new list. Let's just say band 1, blue, oops, green, red, NIR, band 6, band 7. So let's do EP hist, Landsat postfire XR dot values, title equals band titles, and then a PLT dot show. And you can see we got our histogram. Very cool. Let's plot a color infrared image now. So we're gonna again use the plot RGB utility, but instead of passing the red, green, blue layers, we're gonna pass in color infrared. So ep.plot RGB Landsat postfire XR values RGB equals 432 title equals CIR Landsat, and then let's do a PLT.show. Very nice. Cool. So now we won't spend a lot of time thinking about kind of the dates, but the Julian day used to be used in Landsat pre-collections file naming, but they've switched to normal year, month, day format. And so previously they were counting days in a different day, like in day of the year instead of like month, day, year. And so just for older imagery, you might run into weird file names, but it's not too much of an issue for new data. That's really it for this Landsat lesson. So let's save it, commit it to our repo, and keep pushing. I believe this is lesson 5. Yes. Okay, so that's done. Let's double check that it actually updated in our repository. We're good. Okay, now let's continue on and we'll create a repository or create a notebook called Open Landsat. So we'll do touch open landsat.ipynb. Let's open that and then open the lesson. So after this lesson, we're going to be able to create a list of, a subset of Landsat TIFF files with glob, which we kind of already did, but we're going to also learn how to crop data. We'll get some more practice with stacking data and then creating a workflow that efficiently opens, stacks, and cleans Landsat data. So automating your analysis or your data processing. So this is jumping right into code. So let's do it. So let me import a bunch of libraries. Import OS. from glob, import glob. Oops. Import matplotlib.pyplot as plt. Import geopandas as gpd. Import raster.io as rio. Import x array as xr. Import rio x array as rxr. Import numpy as np. Import earthpy as et. Import earthpy spatial as es. Import earthpy.plot as ep from shapely dot geometry. Import mapping. Cool. Have everything imported. Now let's set our working directory. We already have the data downloaded, so we'll just do an os shadir, os path join, etio home, earth analytics data. Okay, so to start, let's kind of do what we were already doing in the last lesson and explore our data with glob. So let's create the base path name for our Landsat post-fire data, which is pretty much a direct copy of what we did last lesson. So Landsat post-fire path equals OS path join Gold Springs Fire Landsat collect. A really long file path that I'm not going to try to type. And then crop. So then if we output this Landsat post fire path, we'll get this. And then if we do an OS list steer on this path, we get all the files contained in that directory, which is awesome. So now we can grab all the files in a different way as well. We can just use glob. And so we'll do glob. And then let's pass in the Landsat post fire path. Actually, oops, let's do OS path join Landsat post fire path and then the wildcard. And so this should output everything in there because we're not specifying anything beyond all the files, because that's kind of what this stands for, anything. If we want, we can subset using a little more nuanced kind of character matching. We could do asterisk.tiff, which only returns TIFF files, which is still kind of everything in that folder. If we only want to grab bands 2 through 5, we could do something like this. Essentially, band 2 to 5 dot diff. This would return just bands 2 through 5. Again, it's unordered because we haven't sorted them yet, but just kind of giving you an idea of how to do such things. And we actually want to save this into a variable. So I'm going to call this all Landsat post bands, because these are the bands that we actually care about for today's lesson. So then let's sort this list. And now you can see that it's sorted in numerical order from 2 through 5. So in the previous lesson, we created a small function that opens a single Landsat band. Let's expand that function to open, crop, and clean data. So to start, let's copy that function from previous lesson. Open, clean band, band path. And it just returns rxr open raster.io band path masked equals true dot squeeze. So let's just make sure that works really quickly. Landsat post XR equals open, clean, and let's just pass in all Landsat bands, but just the first one. And then we can plot that PL or FAX equals PLT subplots Landsat post XR dot plot dot imshow CMAP equals grays R AX equals AX. Let's set the title. Plot of band 2 AX dot set axis off PLT dot show. And we have our plot of band 2. Lovely. So we just opened and plotted a single band. Oftentimes, though, you're going to want to crop your data to the spatial extent of your study area. So cropping removes data you don't need in your analysis, and you could choose to open and crop each file individually using open or using RxR open raster IO alongside the Rio X-array Rio clip function as shown below. And so we need to have a GeoPanda as a shapely object that represents the extent of the area we want to study in our imagery. And so that data also needs to be in the same CRS as our Landsat data. So we're going to clip our data. So let's start by cropping our raster using a shapefile. So I'm going to do fire boundary path equals OS path join Cold Springs fire vector layers fire boundary geomac and then CO cold oops. Oh, that's annoying. Yeah, I'm just going to copy that. .shp. And then we'll read that in with GeoPandas. Fire boundary equals GPD read file fire boundary path. Now let's get the coordinate reference system of our Landsat data. So we'll do that like this. Landsat CRS equals EarthPy spatial CRS check all Landsat post bands. And which one? Band 2. So let's print out the Landsat CRS and the fire boundary CRS. So we'll do Landsat Landsat CRS print fire boundary .crs. So we'll note that they are in different coordinate reference systems. So let's reproject the data to the CRS of our raster data. So we're going to reproject the shapefile or the GeoPandas geodata frame. So we're going to do fire boundary UTM zone 13 equals fire boundary .to CRS Landsat CRS. And let's plot it. Fire boundary UTM zone 13 dot plot and a PLT dot show. And so here we have our study extent. Now let's actually clip our data. So the ideal scenario here is that we clip the data while opening it, and we'll use the from disk equals true, which tells Rio X-ray to only open the data within the clip extent. This will speed up our workflow a bit. So we'll do Landsat post XR clip equals RXR open raster IO all Landsat post bands 0. And then we want to do dot Rio dot clip fire boundary UTM zone 13 dot geometry. And then we want to do a from disk equals true dot squeeze. It's a mouthful. Okay. And then Landsat post XR clip. So we have this new X-array data array. It's a single layer of 44 by 113. Awesome. Let's plot our data. Big or F AX equals PLT subplots. Spelled that wrong. Let's do Landsat post XR clip. Sorry that my phone's ringing. Don't know who that is. Plot dot imshow cmap equals grays r. Then we'll do, oh, then we need an AX equals AX. Let's also do AX set axis off. And then we'll do a plt.show. Cool. You might want to clean this up a bit by masking out values. And so let's do some data cleaning logic. So valid range equals 0 through 10,000. So if valid range mask equals Landsat post XR clip less than valid range 0 or this is going to be a little messy, but builds character. Landsat post XR clip is greater than valid range 1. That's where we want to bring this back. Landsat post XR clip equals Landsat post XR clip where not XR. This is nasty. Mask. See if this works. Okay, cool. Now let's plot this out and hopefully get a nicer data visualization. Landsat post XR clip plot AX equals AX ELT.show. Ooh, got an error. Landsat post XR clip. Did I spell something wrong? Oh yeah, minus X. There we go. So you can see it looks a little better than before. Instead of this kind of like noise of no data, we're actually seeing some variety in the landscape, which is cool. So now let's actually write a function that can clean and crop our Landsat data more seamlessly. So we'll do define open clean band and it'll take a band path, a clip extent, and a valid range as input. And the valid range is optional because it has a default of none. So let's kind of smush some of the previous code cells into a single function so that we don't have to run many cells to do what we want. So we'll try clip bound equals clip extent dot geometry except exception as error print. Oops. I need a geodata frame object for this to work. Print error. And let's actually spell exception correctly. Cleaned band equals RXR, open raster IO. And path masked equals true. Dot Rio dot flip bound from disk equals true. Dot squeeze. And then only mask the data if a valid range tuple is provided. If valid range mask equals Landsat post XR clip less than valid range 0 or Landsat post XR clip greater than valid range 1. And then we can do cleaned and equals Landsat post XR clip dot where not XR where mask true false return clean band. And this needs to be back. There might be a typo here somewhere. We'll find shortly. Looks like it worked. Okay, let's try it out and see if we can streamline the process of cleaning a band. Cleaned band equals open clean band. All Landsat post bands 0. So band 2, fire boundary UTM zone 13 north. Then we'll do a fig x equals PLT subplots. Clean band dot plot. AX equals AX. AX set title. And one plot. AX dot set axis. Off. PLT dot show. So you see we got an error. It's because I forgot to put a comma between these two entries, and we get our beautiful plot with much less code than having to run through this each time. So it's just a nice, more streamlined way of cleaning, cropping, and plotting data. So now let's create our final automated workflow for this lesson. So we're gonna build the entire workflow using a loop. And the ultimate goal is to create a new raster data set, namely an NDVI data product. We're going to dive in more next week on what that is, but we're getting kind of a teaser today of creating those kind of data sets. So let's create a function called process bands. We're going to do, it'll take input paths, a crop layer, and a stack argument, which defaults to false. So we're gonna return either a list of X-array objects or a stacked X-array object. So we'll do all bands equals empty list for I, a band in enumerate paths cleaned equals open clean band, a band crop layer cleaned band equals I plus 1. All bands dot append cleaned. Okay, so if stack is true, then do print I'm stacking your data now, and then stack it using Rio X-array, or just using X-array concat all bands and stack it on the dimension equals band. If it isn't a stack and it's just the default stack is false, else you're going to print returning a list of X array objects. And then you're going to return all bands. Okay, so we have this second function, which actually invokes our open clean band function. So we're kind of doing nested work right now. So let's get into it. Try out our new function. So fire boundary path equals OS path join. Let's bring fire. Oops, I'm just going to copy paste this for the sake of time. Typos. Okay. Now let's read that in with GeoPandas. This might already be a variable in our memory, but it's fine. We can just overwrite it. Tree file, fire boundary path. Okay. Now we can use glob to get our list of the required bands, namely band 2 through 5. And then we'll sort that and reproject things as necessary. So we'll do all Landsat. Spell things correctly. Landsat post bands equals glob os path dot join Landsat post fire path, and then we're going to use the wildcard to get bands 2 through 5 that are of TIFF file type. And then we're going to sort that list. And then we want to convert our fire boundary to the or CRS to this coordinate reference system of the Landsat data. So we'll do Landsat CRS equals Earth by spatial dot CRS check all Landsat post bands, and we'll just do for one of the bands, namely band 2, and then let's do fire boundary UTMZ 13 equals fire boundary dot 2. Spell things correctly. to CRS, Landsat, CRS. Okay. Let's actually process our bands now using our process function. So we'll do post fire stack equals process bands, all Landsat post bands, fire boundary UTM zone 13 stacked equals true. And then let's output the shape of our data set. So you see we get a typo. That's because there's no stacked argument, it's stack. So I just spelled it wrong. So it's stacking our data, and you'll see it's of shape 414 or 444, 113. Now let's actually plot the data that we processed and stacked. Band titles equals blue, green, red, NIR. EP plot bands post fire stack calls equals 2. BLT soup title cleaned and propped Landsat bands BLT.show. Awesome. We got our data cropped and plotted. Super cool. That's it for this lesson. Let's save our changes, commit them to the repo, and push onward. I believe this is lesson 6 for today. Okay. So we should be good here. I'm just refreshing to make sure that it did commit. It did. Awesome. Now let's create a Jupyter notebook called cleaning and get started with cleaning remote sensing data in Python. Clouds, shadows, and cloud masks. So I'll do touch cleaning.ipynb. Let's open that. Open this lesson and just get started. So we're going to describe the impacts of cloud cover on the analysis of remote sensing data. We're going to use masking to remove portions of a spectral data set that are covered by clouds and shadows. And then we're going to define a mask and describe how it can be useful when working with remote sensing data. So satellites are continuously orbiting the Earth, collecting images on our surface, but weather happens. And so that's one of the challenges of remotely sensed data, large clouds and associated shadows that cover study areas. This is something that we're having to deal with our Cold Springs fire, burn scar research. And so let's get some experience working with clouds, shadows, and bad pixels in remote sensing data. So these clouds and atmospheric conditions present a significant challenge when working with multispectral remote sensing data. Extreme cloud cover and shadows can make certain regions unusable because the reflectance values are either washed out too bright or too dark because of shadows. And so let's learn how to use Python to deal with clouds in our remote sensing data. And just want to call out, there's no perfect solution. And this is just one approach. So I'll start with importing some of our favorites. Plot lib.pyplot as DLT or Seaborn. Ooh, I skipped one. Matplot lib, import patches as patches colors. Import Seaborn as SNS. Import NumPy as NV. From NumPy, import MA. Import Xarray as XR. Import Rio Xarray as RXR. Import EarthPy as ET. Import EarthPy.plot as EP. import earth pi.mask as em. And then let's set some prettier plotting with Seaborn. SNS.set style white. SNS.set font scale equals 1.5. And then let's set our working directory os shadir os path join etio.home. Is it earth analytics data? And so I spelled Seaborn incorrectly, which is fine. Seaborn. And now it works. So let's kind of recreate our functions again from the last lessons. If we were really like working on a project, we would have these in a separate file that we could just import and reference. But because we're kind of just working in these notebooks and these little mini lessons, we're having to recreate a lot of stuff. But if you're actually doing this on a project, you would likely have a separate file called utils.py or something, and then you could just import these from there and hit the ground running faster. So let's do define open clean band, and it takes a band path and a crop layer defaulting to none. And then it just returned, oh, it does some logic, namely if crop layer is not none, try flip bound equals crop layer geometry clean band equals RXR open raster IO band path masked equals true dot rio dot clip bound from disk equals true. And then I don't think there's a, oh, and then a dot squeeze also. Dot squeeze. Okay. And then if that doesn't work, if the try is not matched, then exception as spelling as ERR, print. Oops, I need a geodata frame object for this to work. Print pair. And then else cleaned band equals RXR open raster IO band path masked equals true dot squeeze turn cleaned band. Now let's create another function called process bands. Process bands takes paths, crop layer equals none, stack equals false. So all bands equals empty list for I band in enumerate paths cleaned equals open clean band a band crop layer, and then we want to do cleaned and equals I plus 1 all bands dot append cleaned. And then if it's a stack is true, print I'm stacking your data now. And then return XR and cat all bands on the dimension band. Else, if it's not a stack, print turning a list of X array objects. Return all bands. So now we're going to load and plot our Landsat data. Since we're only using the RGB and the NIR bands for this exercise, we're going to use the glob goodness to filter for those. It'll save a lot of time in processing since we're only using those data and saving on our computer's thinking. So let's load in some data. So we'll do Landsat deer path pre equals OS path join. And here I'm going to copy paste because these are slightly long. Actually, I'll just copy one of them. I'll be a good boy. So we'll do Gold Springs Fire, Landsat collect, the long thing that I copy pasted, crop, band, and then this is asterisk, band, square bracket 2-5, square bracket, asterisk dot tiff. And then we want to sort that. Pads 3 equals sorted. Glob Landsat deer path pre. And then we want to process those bands using the function that we just wrote. Process bands. And we're just going to pass in Landsat pads 3 and say stack is true. And then let's just output that to our console. And so you can see I have an error here. Pad, this is not defined. Might have a typo. That's fine. OS path join. Landsat paths pre. Okay, let's just do this line by line to make sure I didn't screw up somewhere. Okay, cool. So it's this process bands. Seems like there's an error there somewhere, which we'll find. So on line 16, it doesn't like this paths because there's no path because it's a path, it's not paths. Interesting. So let me fix that typo. So here, process bands is paths. Let me just fix that name. And now we can run this all in a single cell and it won't give me an annoying error. So here you can see we read in our data or the folder sorted for just the ones we want and process them in like 3 lines, which is really nice. Behind the scenes, there's many more lines happening, but for the sake of code readability, it's nice. So now let's plot our data. So we can do that really quickly using EarthPy plot RGB. EP plot RGB, Landsat pre dot values, RGB equals 210. Title equals Landsat true, color composite. ELT.show. So I got a typo. Apparently there's no plot RBG function. It's plot RGB. So I just spelled it wrong. And note how there's a really fat cloud right here and a shadow as well. So we have to figure out how to deal with this now. So let's learn how to mask a raster with another raster. So we're going to remove the bad pixels from our analysis. In the case of this Landsat data, we're going to identify pixels that are likely representative of cloud cover, shadow, and even water. So when we downloaded dataset from Earth Explorer, which we didn't do yet, but we will do later today. The data came with a processed cloud shadow mask raster layer called Landsat file name pixelqa.tiff. So just replace the name of your Landsat scene with a text Landsat file name above. And so for this class, the layer is this name right here. So let's explore that layer. So we'll open it using Rio X-Array and then plot it with matplotlib. So let me get this going. We'll do Landsat pre CL path equals OS path join. And I'm going to copy paste this because it's a little meaty. Oops, let's delete one of those quotes. Okay. Next, we'll do, let's open the data with Rio X-Array Open Raster IO. Landsat QA equals RXR Open Raster IO. Landsat pre CL path dot squeeze. And then let's create some categories for ourselves. High cloud confidence equals EM dot pixel flags. Oops. Pixel QA. L8. High cloud confidence. Similarly, we'll do something for cloud. Pixel flags. Pixel QA. L8. Cloud. And then we'll do one more for cloud shadow. EM pixel flags. Pixel QA. L8. Cloud shadow. And then let's do all masked values equals cloud shadow plus cloud plus high confidence cloud. And then finally, let's mask the data using the pixel QA layer. So we'll do Landsat pre CL3 Landsat pre.where not Landsat QA is in all masked values. We got an error here. On line 10. Let's see if we need to use an uppercase C for this cloud, and then it's fine. So let's plot our pixel QA layer in matplotlib. So we'll do f(ax) equals plt sub. Actually, we can just do earthpy plot bands, I suppose. EP plot bands. Okay. So you can see that there's some categories of data that kind of describe different stages of maybe bad or unusable. And so we're interested in, namely, cloud shadow, cloud, and high confidence cloud. So let's classify our data into classes and then plot these classes. So let's create we already have the all masked values here. So let's create a cloud mask like this. We'll do CL. Oops, it's not typing. CL mask equals Landsat QA is in all masked. Oops. Values np.unique CL mask. Oops, did not spell that correctly. False true. Okay, now let's plot our reclassified raster. So we'll do big X equals PLT subplots. IM equals x.imshow CL mask CMAP equals PLT CMAP dot get CMAP tab 20B, which is the name of the color map. And then we just need 2 colors for this. C bar equals EP color bar M. C bar dot set ticks 0.25, 0.75. Let's set the Y labels. Y tick labels, clear pixels, cloud / shadow pixels. AX.set title, Landsat cloud mask, light purple pixels will be masked. And then AX.set axis off, PLT.show. And we have a beautiful figure of our cloud mask. And so what does this actually tell us? So we explored the 2 layers that potentially have information about cloud cover. However, what does this really mean? It's letting us know that there's likely some clouds in this area or shadows, and that we should perhaps adjust for those in our data set. And so now let's create a mask layer in Python to crop out these clouded areas from our data. So we'll do that like this. Landsat free CL free equals Landsat free dot where not cloud mask. Cool. Now let's plot this data. EP plot bands. Let's do Landsat pre CL free, and we'll do the 3rd or the 4th layer, starting from 3 or from 0. Phrase, title, Landsat, IR band. And then C bar equals false, PLT.show. Oops. And you can see I got an error because I put in a non-existent color map. Again, a non-existent color map. And there we go. our data has been masked out. You can see here how there's kind of no data. It might be easier to see with RDGN. I don't even know the name. Yeah, so you can see how there's this kind of like empty chunk here that has no color because it's been masked. Awesome. We can also plot red, green, blue data in the same way, which we'll do really quickly, and then we'll finish this lesson. Plot RGB, Landsat, pre, CL free, RGB equals 3, 2, 1. ELT.show. And we have our color infrared image with cloud junk masked out. Let's save our changes, commit them to the repository, and push forward. Finish lesson. What is this, 7? Yes. Okay. Great. Now let's march onward. Create a new notebook called replace.pynd, and we're going to learn how to replace raster cells with values from a different raster data set. So, namely replacing masked values in one X-ray data array with values from another. So let's kind of get back into our data set, reload in a bunch of the libraries we'll need, and the data we'll need. So let's get into it. So we have this replace notebook. We'll start by importing everything we need. Lib.pyplot as DLT, CBOR as SMS, NumPy, import array, from shapely.geometry, import box, import X-ray as XR, import Rio X-ray as RXR, import EarthPy as ET, import EarthPy.spatial as ES, import EarthPy.plot as EP, import EarthPy.mask as EM. I spelled import incorrectly. Import PyProj. Import GeoPandas as GPD. PyProj dot set use global extent, use global context true. Set some styling with Seaborn. Equals 1.5. Let's just download the data just in case. Equals ET data. Get data. Cold Springs Fire. Data 2 equals ET data. Get data. CS test Landsat. And then we'll set the working directory to ETIO home Earth analytics data. Cool. So let's recreate those functions again. Really getting practice. writing Python functions, which is cool. But like I said previously, if you were using this in reality, you would likely have a separate file where you could import these and not have to rewrite it every single time. Okay. So let's start with our define open clean band function, which takes a band path and a crop layer, defaulting to none. So if crop layer is not none, try clip bound equals crop layer dot geometry cleaned band equals RXR open raster IO band path masked equals true dot rio dot clip bound from disk equals true dot squeeze. Next we'll do an exception as print. Oops, I need a geodata frame object for this to work. Print else. Oops. Else clean band equals RXR open raster IO band path masked equals true dot squeeze. Turn cleaned band. Now let's write our second function, process bands, which will open, clean, and crop a list of raster files with Rio X-ray. We'll do define process bands, pads, crop layer equals none, stack equals false. So we'll do all bands is an empty list. Then we'll do for I, a band in enumerate paths cleaned equals open clean and band crop layer cleaned band equals I plus 1 and then all bands dot append cleaned. If stack is true, friends, I'm stacking your data now. And then turn XR concat all bands along the band dimension. Else print returning a list of X array objects. Return all bands. Awesome. So now let's open and process our Landsat data from before the Cold Springs fire. Landsat deer path pre equals OS path join Cold Springs fire Landsat collect this nasty long string, which I'm going to copy paste. Crop. And then the glob friendly pattern matching to only filter down to bands 2 through 4 that are TIFF files. And let's Landsat paths pre equals, so we're going to sort that list now that we're filtering down to. So Landsat ear path pre. And then let's invoke our process bands function to process our data. We want to stack equals true. Landsat pre. Got a typo here because I spelled something incorrectly. It should be sorted, not sort. Nice. Beautiful. 3 bands of data, just as we expect. Now let's mask out our cloudy pixels. So we'll do Landsat pre-CL path equals OS path join Cold Spring Fire Landsat collects that long thing, drop, and then another long name, which I believe is a TIFF file. Okay, cool. TIF. Okay, we're getting there. Let's now open that with Rio X-Array and set QA, RxR, open raster IO, Landsat pre CL path dot squeeze. And then we're gonna create those same categories from the previous lesson of high cloud confidence, cloud, and cloud shadow. So let me briefly code that out. High cloud confidence equals EM pixel flags pixel QA L8 high cloud confidence. Oops. Then I'm going to copy this line 2 more times and then just tweak it as necessary. I'll call this cloud. I'll call this cloud shadow. I'll change this to just cloud. And then I'll change this to just cloud shadow. Spell shadow correctly. Okay. And then we'll create an all masked values variable that is just the sum of all those masks. Cloud shadow plus cloud plus high cloud confidence. And then let's mask the data using our pixel QA layer. Landsat pre-CL masked equals Landsat pre where not Landsat QA dot is in all masked values. Oops. Spilled a bunch of coffee. It's all good. Okay. Fine. I need 1 second to wipe up all the coffee I spilled, and I'll be right back. Still muted, was talking. Did not realize I was muted. My bad. All right, so I've cleaned up some of my mess of coffee that I spilled everywhere. My shirt is nice and damp and coffee, but we're getting back into it. So now let's read and stack cloud-free data. So we've been using Landsat scene with a large block of cloud-covered pixels. So now let's fill these pixels by replacing them with pixels from another Landsat scene that covers the same area during a similar time period. So we're going to read in and stack the cloud-free Landsat data. And then we're going to clip our cloud-free Landsat scene to the same extent. So let's get that going. I'm having like traumatic stress. I'm going to knock over my coffee again. Okay. Landsat pre-cloud ext PDS. Lans pre dot Rio dot bounds. Let me change that lowercase. Okay. And then let's create a new data frame. And then we'll clip our data. So we'll do df equals ID 1 geometry box Landsat pre.rio.bounds. So we're creating a box around our Landsat data to filter our data more. So actually, this needs to be a dictionary and not a list. There we go. And then let's do clip GDF equals GPD geo data frame df, and we want to set the coordinate reference system to that of the Landsat pre CRS. And then we can plot our data. Clip GDF.plot plt.show. And we have a square or a rectangle to be more precise. So now let's read in our cloud-free data and try to merge the data sets to make a nicer image. So we'll start by reading in the cloud-free Landsat data set that we downloaded already. Cloud-free path equals OS path join CS test Landsat. And then this pattern band 2 to 4. That's a type TIFF. And then we'll do Landsat as pre cloud free equals sorted blob cloud free path. Okay. Now let's process our bands using our process bands function. So we'll do Landsat pre cloud free equals process bands Landsat as pre cloud free stack equals oops true crop layer equals clip GDF. And then let's output this data set. Rio, or it's an X-array data array, just as we expected. Perfect. So let's check that the spatial extents are similar. And then we can continue on. Landsat no, oops. Landsat no clouds BDS equals Landsat pre-cloud ext BDS. Oh, I forgot to. Okay, that's why. So let's do, does Landsat pre-cloud free Rio bounds equals Landsat pre Rio bounds? True. Okay, so the bounds are the same. Or no, the bounds of each data set are different. Weird. Even though they're saying the bounds are the same. So let's actually print out the bounds. I think that's like a weird typo. So this is saying it's these here. They're actually the same. Never mind. Okay, cool. So let's plot, or let's replace the values of our data with all the cloud information using the new data. So we'll use the where function from Xarray. Mask equals Landsat pre CL masked that is null. I'm going to do Landsat pre clouds build equals XR where mask Landsat pre cloud pre and Landsat pre, don't even know what that says here, CL masked. And then let's output this new data array. Awesome. And then finally, let's plot our data, where we kind of replaced our masked information with data from another image. Plot RGB, Landsat pre-clouds build values. RGB equals 210. Title equals masked Landsat CIR. ELT.show. I keep putting RBG instead of RGB. Plot RGB, and then this needs to be RGB as well. And there's no PLRT function, but you can see we've kind of filled in where the clouds were, and now our data looks a little more presentable. It's not perfect, but you can see that maybe for like a figure or like a presentation, it's a little better than just having massive masks like clouds. Let's save changes to this one. Push on. Lesson 8. Okay. Nice. We have our new notebook added. Let's now create a notebook called Download Landsat. IPYNB. Awesome. I'm going to open this and then we'll jump in. So in this lesson, it's similar to the one for the NAIP. We're going to download data from the USGS Earth Explorer website, filter by cloud cover to find data sets with the least amount of clouds for a study area. So we're not going to actually do this in class today, kind of similar to the NAIP where you could do it after. I just want to, at a high level, walk through the steps. Like with the NAIP data download, you need to define a study area or area of interest. And the textbook has provided you with a zipped shapefile to use for this purpose. Make sure you have an account and you can upload that file easily and specify which data from within that study zone you want to download. For this lesson 9, we want to download Landsat Collection 1 Level 2 on demand. And then to further define the selection criteria, you want to specify less than 20% cloud cover and see what you get as data results. And then order your data. And it should be free. Ordering is not like payment, but it's just a process. So make sure that you follow that. So we'll just say print Earth Explorer for the win. Let's save those changes, commit them to our repository, and move on to the last lesson of the day. Finish lesson 9. Okay, let's refresh just to make sure it's there. It is. So to finish off today, we'll create a notebook called practice.ipynb. And this is practicing opening and plotting Landsat data with raster.io. It's kind of more of what we've been doing today, but it's like a final practice session. So let's do it. It's just straight into code. And let's get on. Import OS. From glob, import glob. Import matplotlib.pyplot as BLT. Import geopandas as GPD. Import Rio X-ray as RXR. Import X-ray as XR. From shapely.geometry, import mapping. Excuse me. Import NumPy as NP. Import numpy.ma as MA. Import earthpy as ET. Import earthpy.spatial as ES, and import earthpy.plot as EP. And then finally, we'll set the working directory, OS shadir, OS path join, ETIO home, Earth Analytics. So let's open and crop some data. Actually, I'm not going to do these with you. These are more like challenges. And so I encourage you to work through these using the previous 8 lessons to help you get through, 2 of which were kind of more just Earth Explorer specific. So the 6 lessons that did require code, or even less than that, because some of them were just printing. But through the lessons that we covered today, you should be able to do these examples. And so we'll say print, do challenge 1 here. And then we'll do print, do challenge 2 here. And so I encourage you to do the challenges and get more practice with plotting data, specifying which bands to plot. So that's actually it for today. So I'm going to save these changes, commit them to the repo, and then kind of just open it up for questions for the remainder of class and let you all kind of trickle out as desired. Lab 10. Cool. Are there any questions on the labs from today? Lecture, content, what's expected for the rest of the semester? Are we're pretty good?
So you said that next week's lab, you'd possibly make it an extra credit opportunity?
Possibly, yeah. Depending on basically the vibe check before class next week. We're still gonna at least show up and do it, but it might be like extra credit. It kind of just depends on how people are feeling next week.
Okay, gotcha. Yeah, I think I mentioned this to you a couple weeks ago, but me and Ritu are actually going to be leaving this Wednesday. Just for the field work for our project. So we'd miss week 6 and the final.
Okay, cool. I mean, you'll have internet access, right? And so I think you'll still be able to do it async. Um, but I would say, yeah, I'll release them as the weeks come out. But I think that it shouldn't be too much of a stress, to be honest, even when you're traveling. Um, is it still on? I thought that like all that stuff would get canceled because of the ongoing um, war
So yeah,
/ genocide.
yeah, thinking the same thing, but event at the end it ended up going through. They like were like it should be fine. The
Yeah.
area and yeah.
Okay, be safe, dude.
Thanks.
Yeah, but okay. But yeah, you should be fine with the assignments. The lab, like the final is pretty chill, to be honest. It's really just this lab and the next week. Yeah.
Of course. All right. Thanks, Alex. That was just the only thing I was
Okay,
really
cool. Yeah.
worried.
No, safe travels, and you can still reach me by email. I
Yeah.
find like async is cool too. Yeah.
Okay. Cool.
Yeah.
All right. Thanks. Take care.
You too. Peace. And that is class. See you next week.